So now we will start the another chapter which is very important for that point of view, that is refrigeration. So we will talk about refrigeration. So first of all I will write the simple definition of refrigeration and then we will see the fundamentals regarding refrigeration. So first of all let's start with refrigeration. So refrigeration is nothing but a cooling of a system below the temperature of its surrounding. So I can write refrigeration is the cooling of a system below the below the temperature of its surrounding. So refrigeration generally deals with the cooling process by which we can cool the system below the temperature of the surrounding. So let's draw a simple refrigeration system here. So for refrigerator, first time this one is the source which is having the temperature T1. This one is source here. Now we are having this one called refrigerator. Here we are doing some work on it, that is W, and then we are having sink, that is having lower temperature T2 sink. So as far as first law of thermodynamics or zeroth law of thermodynamics, the heat will flow from a higher body to a lower body, but here what we are doing, we are extracting heat from the cold body and we are rejecting heat to a hot body. So here we are doing the inverse process. So in that case, so definitely we have to do some work on the system, then only it is possible. So it's a typical refrigeration system here, and here we are interested in Q2 because our primary interest is to lower the system, the temperature of the system below the temperature of the surrounding. So surrounding in that case will be at higher temperature. This one is surrounding, but our interest here is for Q2. So in case of refrigeration, we are interested in COP rather than efficiency. So I will write for refrigerator or refrigerator, and here I will same cycle I can use for heat pump also. Heat pump. So here both the process can be shown by this block diagram, but the interest is different. In refrigerator our interest in on Q2, but in pump our interest is on Q1. So I can write refrigerator interest is Q2 and heat pump interest is Q1. So now if we write the COP, so we have to consider Q2 divided by W, and we know the W we can write Q2, W is Q1 minus Q2. Similarly for heat pump COP, this is the COP of refrigerator and this one is the COP of heat pump. So our interest is Q1 divided by W. So Q1 by Q1 minus Q2. So this one is the basic difference between the refrigerator and heat pump. But remember one thing, the cycle here, whatever I shown, this is the same cycle which can be used for refrigerator and heat pump. Only the difference in our interest. In refrigerator, I will again repeat, we are interested in Q2, but in heat pump, we are interested in Q1. So now We will find the relationship between COP of heat pump and COP of refrigerator. So I am writing the COP of heat pump equals to Q1 minus Q2. So now if I add this thing here, that is COP of heat pump and COP of refrigerator, I am having COP of refrigerator, that is Q2 upon Q1 minus Q2. So now if you see these two formulas, then I can write COP of heat pump equals to COP of refrigerator plus 1. If we add plus 1 here, then definitely we will get Q1 by Q1 minus Q2. This one is a very important relationship. COP of heat pump is always better than by 1 with COP of refrigerator. Now let's talk about reverse Carnot cycle. Reverse Carnot cycle. So first I will explain the process with the help of block diagram and then I will plot the process of the TS diagram. So here we are having the 4 component. First I will draw the component. Here this one is condenser. This one is our compressor. This one is our evaporator. And this one is our expansion device. This one is our expansion device. So I will again write the name here. It is condenser. Condenser. Here we are having compressor. Compressor. Here I am having evaporator. And here I am having expansion device. Expansion device. So now I will explain the process. So here the gas will enter into the compressor. So here it will enter at a point 1 and after compressing it will leave to the compressor at point 2 and then from 2 to 3 it will go into the condenser. It is going into the condenser from 2 to 3. So now at 3 it is going from 2 to 3 in a condenser and then it will enter into the expansion device and it will leave at a point 4 and then it will enter into the evaporator and it will leave at a point 1. So here we have to do work on the compressor, that is WC, Q1 that is a heat rejection here, Q2 here and WE that is our WE. So now I will show this reverse Carnot cycle on the TS diagram for our better understanding. So let's talk about this thing on TS diagram. This one is the TS diagram for that. Here we are having the state 1 and from 1 to 2 we are compressing, that is isentropic compression from 1 to 2. 2 to 3 will be in condenser. So if you see 2 is a saturated vapor state, 3 is a saturated liquid state and again from 3 to 4 it is expanding in an expansion device and we are getting point 4 here. So this one is a typical process on the TS diagram. So this one is a typical process here. and here the temperature is T1 and here the temperature is T2. So uh, this one is a typical representation of a Carnot cycle on TS diagram, and we know this thing. The Carnot cycle is a reversible cycle. So instead of heat, we can also use the temperature. So for COP, for refrigeration, in that case, I will write for reverse Carnot cycle. Reverse Carnot cycle. I can write it is nothing but Q2 Q2 divided by Q1 minus Q2 equals to T2 divided by T1 minus T2. Similarly, I can also write for heat pump here, COP of heat pump. In that case will be Q1 divided by Q1 minus Q2 equals to T1 divided by T1 minus T2. So this one is useful when the cycle is reverse cycle, and all the process are reversible process. So we can use the temperature in place of heat. So this one was the mathematical representation. But if you see the whole process from here, if we start from here, that is 1 to 2. If you see in a TS diagram, 1 we are having the mixture of vapor and liquid, but due to this isentropic compression, we are having a saturated uh, vapor here, and from 2 to 3, its one is a it is a process in condenser, that is from 2 to 3 here. So 2 to 3 we will get the saturated liquid at a point 3, and we are expanding it in an expander. The use of the expander is we have to decrease the pressure here. So we are decreasing the pressure from 3 to 4, as well as we are decreasing the temperature here. So we will get again a mixture of we will get again the mixture of saturated vapor, and we will get the mixture of vapor and liquid here, and from 4 to 1 it is in evaporator. So in this process it will take the heat from the surrounding. So this the phase will change, means here if you see the quantity the quality of the mixture, here it is suppose x, so here at 1 it will be more than x, means the liquid is converting into the vapor here. So this is the typical process. Now let's take a vapor compression refrigeration system, which is very important for gate point of view. So I will talk about vapor compression refrigeration cycle. Refrigeration cycle. So the vapor compression refrigeration cycle, that is widely used in all refrigerating system. So first I will draw the refrigerator vapor compression refrigeration cycle. It is same whatever we discussed in Carnot cycle. So again I will draw this thing. Here we are having the compressor on which we are doing the work, and now entering at state 1 and leaving at the state 2, and after leaving from the compressor it will enter into the condenser. So this one is the condenser, and from condenser the same saturated liquid will come out from the condenser at point 3, and it will expand in an expansion valve. Expand in an expansion valve here, and will leave at state 4 from the expansion valve, and it will enter into the evaporator, and from evaporator it will leave at state 1 and it will again enter into the compressor. So this one is compressor, This one is condenser. This one is expansion valve. Expansion valve. Or we can say that it's a throttle. So this expansion valve is helpful in reducing the pressure of the refrigerant. So I will talk about this expansion valve. Expansion valve reduces the pressure, reduces the pressure of the of the refrigerant. So basically for vapor compression cycle, we are using two kinds of expansion device. For vapor compression cycle, we use two types of expansion valve. The one is capillary tube, that is used for small units, used for small units. Second one, the throttle valve. It is used for large unit. So basically expansion valve we are using for reducing the pressure here from condenser pressure to the evaporator pressure. This one is the evaporator. So from reducing pressure from condenser to evaporator we are using this expansion valve. So capillary tube used for the small units and throttle valve is used for large units. Now I will show the representation of vapor compression cycle on PV, TS and HS diagram. So representation of vapor compression refrigeration cycle on PV, TS and HS diagram. So let's take a PV diagram. So now I will draw the processes on PV diagram here. So first of all I will draw the dome first. If you see in compressor, that is isentropic compression from 1 to 2. So isentropic compression I am representing here from 1 to 2. This one is the isentropic compression, that is from 1 to 2. Here the entropy is constant. From 2 to 3 it's a constant pressure heat rejection. So 2 to 3 constant pressure heat rejection, and 3 that is a saturated liquid state. So we are having at point 3 that is saturated liquid. 3 to 4 it's a kind of throttling process where we are reducing the pressure from condenser pressure to evaporator pressure. It's a kind of irreversible process, but in that process enthalpy will remain constant. So I am representing 3 to 4 process here. This is 3 to 4 process, and 4 to 1 that is in evaporator, that is the heat addition in evaporator, that is 4 to 1. So this one is a typical representation of vapor compression refrigeration cycle on PV diagram. So here from 3 to 4 enthalpy is constant. In similar manner we can also represent this cycle on TS diagram. So now For TS diagram, we already know this one is the dome. And 1 to 2, we know that is isentropic process, so enthalpy will remain constant. So this one is 1 to 2 process. And 2 to 3, it is in condenser, that is constant pressure heat rejection. So it's a constant pressure heat rejection here. So the temperature will decrease and we are getting saturated liquid at step 3. 3 to 4, that is a throttling process, constant enthalpy process or irreversible process. So I will represent by this way, that is 3 to 4, that is H equals to C, and 1 to 2 S equals to C, and 4 to 1, that is in evaporate, 4 to 1. So this one is a typical representation of vapor compression refrigeration cycle on TS diagram. In similar manner, I can also draw the curve or vapor compression refrigeration cycle on enthalpy entropy diagram. So this one is a typical enthalpy entropy dome. Here 1 to 2 we know it's a constant entropy process, that is isentropic process, S equals to C. 2 to 3 is a constant pressure heat rejection. So this one is a constant pressure heat rejection. At 3 we are at the state of saturated liquid. 3 to 4, it's nothing but constant enthalpy process, or we can say that it's a irreversible process. So 3 to 4 we are having constant. So I will represent here somehow. So it's a 3 to 4 constant enthalpy process, and then 4 to 1 again, it's a kind of heat addition process, that is a constant pressure heat addition, is 4 to 1. So 4 to 1 here. So here I will again draw the HS diagram for our clear understanding. So HS diagram, because this 4-1 is also looking horizontal, so I will make it clear in my other diagram. So first I will represent this 3. So here it is 3, we go like 4. Okay, here I am putting 1. So 1 to 2, it's a isentropic compression, S equals to C. 2 to 3, constant pressure heat rejection, that is 2 to 3. So 2 to 3 is a constant pressure heat rejection, it's 2 to 3. And 3 to 4 is a constant enthalpy process, 3 to 4, and 4 to 1 again constant pressure heat addition. So 3 to 4, that is a constant enthalpy process, 4 to 1 again it's a constant pressure heat addition. So it's a typical representation of vapor compression refrigeration cycle on HS diagram. Now I will write the steady flow energy equation for all components. So steady flow energy equation for, let's start with compressor. So here we will get H1 plus WC equals to H2. So we can calculate WC is nothing but H2 minus H1 in terms of kilojoule per kg. Similarly, for condenser, steady flow energy equation for condenser. So I will write H2 equals to Q1 plus H3. So Q1 will be H2 minus H3 kilojoule per kg. Steady flow energy equation for expansion valve. Expansion valve. It may be capillary tube or throttle valve depending on the application. So expansion valve. It's a constant enthalpy process. H equals to C. So I can write H3 equals to H4. Steady flow energy equation for evaporator. Evaporator. So I can write H4 plus Q2 equals to H1. So Q2 equals to H1 minus H4 kilojoule per kg. And I have already talked like in refrigeration system we are interested in Q2. So this Q2 is also known as refrigerating effect. Q2 equals to H1 minus H4 is also known as refrigerating effect. Refrigerating effect, that is nothing but the the amount of heat removed, amount of heat removed, amount of heat removed from the surrounding per unit mass of per unit mass flow of refrigerant. So the refrigerant is nothing but the working fluid for this refrigeration cycle. So now let's talk about COP. So COP we can write Q2 by work. So that is compressor work. So Q2, in place of Q2 I can write H1 minus H4, and in terms of W, that is compressor work, so H2 minus H1. So by this way we can calculate the COP. And now if we are interested in if the mass flow of refrigerant is given, so the rate of heat removal we can find out by a different formula also. If W is the mass flow of refrigerant in kg per second, then the rate of heat removal, the rate of heat removal from the the surrounding will be W H1 minus H4 kilojoule per second, or we can say W H1 minus H4 into 3600, it will be in kilojoule per hour. Now I will discuss about capacity of the refrigerating plant. So now we will discuss about capacity of the refrigerating plant. So the capacity of refrigerating plant is generally defined in terms of tons of refrigeration. So I will define the 1 ton of refrigeration. So now we are interested in what is the meaning of 1 ton of refrigeration. So 1 ton, I am writing the definition. 1 ton of refrigeration, 1 ton of refrigeration is defined as the rate of heat removal from the surrounding equivalent to the heat required for melting 1 ton of ice 1 ton of ice in 1 day. I will again repeat the definition. 1 ton of refrigeration is defined as the rate of heat removal from the surrounding equivalent to heat required for melting 1 ton of ice in 1 day. If the latent heat of fusion of ice is taken as 336 kilojoule per kg, then 1 ton then 1 ton is is equivalent to heat removal heat at the rate of 1000 into 336 by 24 or 14,000 kilojoule per hour.